Hey everyone, I'm Nick from Coffee Before Art, and in this episode of C++ Crash Course, we're going to be talking about the new execution policies in C++ and how we can get some, basically free vectorization and parallelization of our normal algorithms that we use from the C++ standard library. Right, so with C++ 17, we got execution policies, right? So we got sequenced, parallel, and parallel unsequenced, and then, as C++ 20 gets finalized, we'll even get the unsequenced policy, right? And so these are basically things that we can pass into our normal algorithms like reduce or sort to take advantage of some pre-optimizations, right? So here we'll look at a very simple example in this parallel algorithms.cpp, right? So we'll need to include this execution header, and what we're going to be doing, right, is a very simple operation here, which is we'll create a vector of between 2 to the 15 and 2 to the 22 elements. So we'll test all of these using Google Benchmark, and then what we'll do is we'll just call reduce on them from the standard library. Except instead of just calling as normal v.begin, v.end, right? So basically the iterators to the beginning and the end of our container. We'll also pass in an execution policy. So here in this sequence bench, right, we'll pass in standard execution SEQ, right, for sequenced. Now, sequence execution is basically like we call this without an execution policy, right? So just kind of the normal sequential execution. But, we can also have a parallel execution policy that we specify with this PAR pair. So what this does is it says that, okay, this operation we're doing with this standard library function, right, so reduce, try to parallelize this. Now, it doesn't say that it necessarily will be parallelized. So things like thread creation may just be something that's too expensive to do. For maybe you only have a vector of, say, 2 elements, right? So if you only have 2 elements, you probably don't want to be spawning a thread, in order to sort things. So it might decide for you, well, it's kind of an unwise decision. But it says that if it can, it will try to, right? And this is all built upon TBB, which is Intel's thread building blocks. So the next thing, right, we'll use the parallel unsequenced execution policy. Now, we already got some parallelism out of this, but now we can also get some vectorization as well. So we can get some data level parallelism going, right? And so we use that with this par unseq or unsec execution policy here, right? So we'll test all of these out with the reduce option or the reduce execution or reduce algorithm, and then we'll go ahead and try this, like I said, between 2 to the 15 and 2 to the 22 integers, right? So in order to compile this, there's a couple of things that dependencies that we have to have. So one, we need Intel thread building blocks to be installed, and we need to link against it. So I'll go ahead and link the instructions for setting that up in the description, and then of course we're using Google Benchmark, so we'll need that as well. Another thing we'll need is that this is only implemented in GCC 9.1, right? So I'll be using G++ 9.1 here. So to actually compile this example, right? So we'll go and look at this command, right? So G++, right? And remember this is G++ 9.1. Right, we need to set the standard to be C++ 17. This lib benchmark and lib pthread, these are related to Google Benchmark. And then for our new execution policies, right, we need to link against Intel thread building blocks. So we do -l-tbb, and then we can just output our parallel algorithms. Right, so we'll go ahead and compile this. And let's go ahead and run it. So again, it's between 32K elements and 4 meg of elements, right? So 2 to the 22. So here we get a rough idea of the performance. So here we've got for 32K elements of integers, right? Reducing them, it's about 0.386 milliseconds. Getting down here to parallel bench, right? So this is where we gave the parallel execution policy. We're down to for the smallest case 0.152. Right, and then over here for the parallel unsequenced bench, so this is where we may also get some vectorization, we're down to 0.121 for the smallest, right? But we see the largest benefit at the largest size in this case, right? So here we've got parallel unsequenced at 2 to the 22 elements, so this only took us 7.36 milliseconds, a little bit longer at just the parallel execution policy at 11.1, and then both of these, of course, are much faster than the normal sequential version or sequenced one. at 49.6 milliseconds, right? So just by using our normal standard library algorithms and passing in a different execution policy, right, we can get some great speedups for our code. So if we have code that's already using these standard library functions, we might as well, if it makes sense, try to use these new execution policies, right? There are a couple things about these execution policies that we should know, right? So if we want to have, parallelism and we want to specify our own function, say in a for each loop, right? We want to, pass in some, lambda that does something. It's up to us, the programmer, to make sure that we don't have any data races in the data that we're actually processing, right? So that's something that's up to the programmer, right? The runtime can't make sure that you don't have any data races or predict your data races that were built into the code. But the nice thing is that this just kind of works for most things. So let's say instead of doing reduce, we want to do something like sort, right? So let's go ahead and sort numbers between 0 and int max. All we need to do here, right? So we'll just comment out some of the things dealing with reduction, right? And we'll just change reduce here to sort, right? And here we've got, that's for the sequenced one. Then we'll go ahead and do that for the parallel one. So we'll get rid of this and we'll just change it to sort. And like I said, we'll just do it for the last one as well. So we'll get rid of this unused value now and then change reduce to sort, right? So let's go ahead and compile this again, right? And now we can run it, right? And this time we're sorting algorithms, right? Or we're using a sorting algorithm instead of using a instead of doing a reduction, right? So you see it takes quite a bit longer, right, for sorting, right? Reduction is a lot easier than sorting. So here we've got, right, all the way up to about 1,500 or so milliseconds when we're at 2 to the 22, and you see that once we parallelize it, we get all the way down to 116 milliseconds, right? So this is roughly 15 times faster by just passing in a new execution policy. And you see we actually don't get any benefit from this parallel unsequence, so whether or not it was able to vectorize anything, unlikely it was able to, it's probably unlikely it actually did any vectorization. It just said, okay, well, there's nothing really to use any of the SIMD hardware here for, so I'll just keep it as just parallel, right? So you see that you get very similar performance. So 117 milliseconds versus 116. But again, all we had to do here was pass in a new execution policy. But that's going to go ahead and do it for this video. This is just a brief introduction to the new execution policies as part of C++ 17 and is implemented using Intel Thread building blocks in GCC G++ 9.1. Right, so feel free to check out any of the other content on this series at github.com/coffeebeforearch. So we looked at optimizations today, right, and this is going to be under parallel algorithms. So again, feel free to download this, check this out. Let me know if you have any questions, and as always, I'm Nick, and I hope you have a nice day.